just want to briefly review the stuff that we covered already and also correct 2 Blackboard brain death incidents that I had yesterday. One was that for some reason I thought I wrote the convolution theorem wrong. I don't know why I thought that. I wrote it correctly. So it's okay. Don't worry. The other thing was that I forget who, but somebody asked about normalization of the definition of convolution. And I sort of got flustered and didn't understand what the question was about. I think what the person was asking about was just that sometimes people see like a factor of 2 pi or square root of 2 pi in front of this. Is that true, whoever was asking? Okay, if not, then it doesn't matter. Okay, but yeah, sometimes when you see the mathematical definition of convolution, it'll have a factor of 2 pi or square root of 2 pi in front. And this is part convention and part depending on how you define like time or frequency. So don't worry too much about it, but I just wanted to sort of make sure that if someone was confused, yeah, mention that. Okay, so to briefly review, we talked about the motivation for using the Lomb Scargle periodigram in the first place. I showed you this sort of super messy data set that had, heteroscedasticity, non-uniform sampling, these periodic gaps in the data, all these things that make it really difficult to just take a Fourier transform and interpret it. You need some non-standard tools, so that's where the Lomb Scargle periodigram is going to come in. We reviewed 2 different aspects of the continuous Fourier transform in order to sort of set up the stuff that we need for the Lomb Scargle periodigram. One was the idea of the power spectral density and the difference between the power spectral density and the Fourier transform. So I wrote out this little thing that showed you that while the Fourier transform itself is in general a complex number and it can be negative and positive and have imaginary and real values, the power spectral density is a purely real, purely positive number, and it doesn't care about time shifts. So no matter where your periodic signal starts in time, you're going to get the same power spectral density. So that's really helpful for a lot of astronomical applications because often we care not about when the signal started, if it started, now or 10 minutes from now, but what the actual underlying periodicity is. I also talked about the convolution theorem, which underlies a lot of the visualizations that I showed you and I'm going to show you for the rest of the lesson. So I talked about the mathematical definition of convolution, reviewing what Brian said about the idea of 2 functions sliding past each other, and then also went over the convolution theorem, which is that the convolution of 2 functions in time space is the same as the pointwise product of 2 functions in frequency space or Fourier space, and the vice versa is also true. That the convolution of that the pointwise product of 2 functions in time space is the same as the convolution of two functions in Fourier space or frequency space. The next thing we talked about was the effect of a uniform observing window. And so the goal of this little section was to derive, okay, if we have this infinite continuous signal that goes on forever, and we observe it only during a finite observing window, how is that going to affect the time domain thing that we observe, and also the Fourier transform of what we observe? So we reasoned through this that here's the Fourier transform of the actual underlying signal, here's the Fourier transform of our window function, and then we use the convolution theorem to sort of walk through, okay, the actual observed Fourier transform you can derive by just sliding the window function Fourier transform past the actual underlying Fourier transform. And so you end up with this thing, which looks pretty similar to this guy, except we've got this sort of wide and sort of wiggly window function pattern imprinted on the underlying data. Okay, so I think the last thing we were talking about was the effect of observing a continuous signal at an infinitely repeating, but specific points in time. So you can approximate this by having like an infinite sequence of repeating delta functions to represent your window function. And you can simulate the effect of actually observing this signal, which I was imagining as the thing passing in front of the other thing, gravitational lensing. A gravitational lensing signal. So if you imagine taking this gravitational lensing signal in time and taking the pointwise product with this comb of delta functions, here's what your actual observing pattern will look like. And then we reasoned through the effect that this would have on the actual observed Fourier transform by observing the Fourier transform of the signal itself, the Fourier transform of the window function, and then taking the convolution of these two. So passing that Gaussian thing past the sequence of delta functions and getting this series of repeating Gaussian-like things. So these things are called aliases of the true signal. So Brian mentioned that term yesterday as well. So these are, if you were to just look at the observed Fourier transform, you can't distinguish whether this one is the real one or this one is the real underlying signal. It's a product of the sampling pattern that we used. Okay, so I'm going to go on to the next part of the section. This was all just sort of a recap of what we did yesterday. Are there any questions so far before I keep going? Okay, can I also get a quick, like, how do you feel about the content so far? Are you understanding it or not? Can you do a thumbs up if it's great, thumbs to the side, or thumbs down? Okay, cool, thanks. Appreciate your honesty. Okay, so let's keep going. So the next thing we're going to talk about is the effect of non-uniform sampling. And this is, we're sort of inching closer to real observing conditions. We've gotten to a uniform observing window where we're not observing this thing, over forever, where we only have a certain amount of time that we can observe it in. We've also talked about observing at specific infinitely thin in time points. And now we're going to talk about, okay, what if these points aren't actually uniformly spaced? What if we observe them at this sort of random pattern? And this is true in astronomy. Like oftentimes, maybe the weather's really good and we get a couple of observations in a row, and then there's some clouds for a while and we can't observe maybe this region here. And then we try to get something that's pretty, uniform for a while, and then the weather is great again. So, so there's all sorts of things that happen that make these sorts of very random patterns very realistic. So we can reason through using the same method how this will affect our actual observed signal in the time domain and in the Fourier domain. So the Fourier transform of our underlying true signal is the same Gaussian thing. And then the Fourier transform of random noise is random noise. I think that's a Fourier pair that's often left out of like intro, like Fourier transform of a Gaussian is a Gaussian, Fourier transform of the top hat is a sinc function. I think they should add Fourier transform of random noise as random noise, because that's really an important one. So the other feature of this Fourier transform that you might notice is that it has this very sort of thin peak around 0. And that's related to the fact that we're observing this over a finite window as well. So things in time space that have like wide widths in time space end up with small widths in frequency space. So the thing that's thin here is coming from some wide thing in time space. But yeah, the main point here is that this is a random sequence of observations, and so that's giving us this sort of random series of peaks in Fourier space. So now reasoning through how this actually affects us, the pointwise product of these two gives you this observation of the signal. So you can see we've got the overall pattern of the increasing thing over time, and where you've got more a higher cadence of observing data, you see there's more samples here. And then the Fourier transform of this we can get by convolving our actual underlying signal with our window function. So we're going to slide one past the other, we'll get this. So you might notice that, first of all, the sort of characteristic width of each of these peaks is similar to the characteristic width of the signal. In general, it's going to be whichever one's wider, the characteristic signal in the window function or in the actual signal. And there's also this sort of randomish looking noise that's sort of maintained. The other thing you might notice is that this doesn't look super clear. It's not really obvious from this. You wouldn't look at this and say, oh, of course, it's this, underlying true Fourier transform. So this is a product of the fact that we don't have, perfect sampling. If we had, it's a product of the fact that our sampling isn't perfect. So at this point, I was going to ask you a question, but I know that you've all scrolled through this already. So it might give away the answer a little bit. But so what I was going to ask is that if you were a time series observer and you knew that this, you somehow knew that this gravitational lensing event was going to happen, what would you want to do in an ideal world in order to get a better representation of the underlying signal? Sorry. Exactly. Yeah, you would want to observe it more. So you would want to make sure that you're observing, as uniformly as possible within this window. So that's exactly what we would want to do. We want to increase the sampling cadence. And as you sort of expect, this will make our signal and the Fourier transform of our signal look more like the underlying reality. So you can see that we've still got this similar pattern of sort of noisy stuff, and then this peak around, this narrow peak around 0. The pointwise product of our actual observing window function and the underlying true data is going to start to look more like the real underlying signal. And then if we convolve our signal in our window function, we can get the expectation. We can figure out what the convolution, what the Fourier transform of the actual signal should look like. And you can see that this guy looks a lot more similar to the true underlying signal, as we expect. We expect that if we observe more, we get a better representation of the underlying signal. But the fact that we're not observing uniformly means that we're always going to have this sort of noisy floor. So that's a general fact of life, is that when you're observing in a non-uniform way, you're always going to get noise in the Fourier transform. Okay, so the last section that I want to take you through is completing the jump to real observing conditions, or realistic observing conditions. So I was proud of this intro sentence. Many astronomical observations are neither uniform nor non-uniform, but a secret third thing, semi-uniform. Thanks. I know it's 9 a.m., but I appreciate it a lot. So this means that there are periodic patterns in your data, but they're not perfectly periodic. There's randomness within that periodicity. So, for example, when you're observing from the ground, you can only see stars during the night. So your observing cadence might look like, uniform random samples throughout the night, but you can't observe it all during the day. So that's going to imprint a daily periodicity into your window function, but it's not going to be a perfect daily periodicity. It's going to have some randomness on top of that. So I want to give you an example of how this manifests in real data. So this is a window function. So just to remind you, just to make the connection to what we've been looking at before, this is this panel that we've been looking at in these 6 panel bins. So this is the Fourier transform of, it's this guy. So it's in time space. So this is period. No, sorry. It's just the period is the x-axis. So it's still this guy, it's just in period space rather than frequency space. So this is the window function, and we're looking at patterns in the Fourier transform of the window function. So yeah, again, I know that you guys have sort of scrolled through this and maybe you've identified these already, but I want to ask the question, what patterns do you see and how do you think you can explain each of these peaks? So what's one pattern that you see or one peak that you see?
So it's like one day, half a day, maybe that's the conics of the day.
Yep, yeah, exactly. So this is the one day. And then exactly like you said, it's 1 over integer values of the day. So 1 over 2, 1 over 3, 1 over 4. Yeah. So how do you think you explain any one of those?
The half day would be like the alias or the alias peaks. But I'm surprised why there isn't 2 or 3 days. I can't really explain that very well, actually. Why there isn't like...
Yeah, so you can think of the window function like a separation between data points that you often see. So between like successive data points. So if you observe like every single day, the successive distance between data points will always be something like a day, and we'll never get up to 2 days. So you might expect to see a 2-day peak if, for example, you have weather that's poor on a 2-day time basis in your observation. So you can only observe every second day. Or maybe it's the fact that something that's from scheduling. Maybe the instrument's only on the telescope every 2 days or something like that. Yeah, good, great question. Thanks for bringing that up. What's another feature that you all see? Yep. Sorry. Yep, it's got a big peak at around a year, exactly. So that's the sky around 365 days. So what do you think that could be from? Yep, yeah, exactly. So the star is only going to be up about half the year. So you'll have this yearly cadence of when observations are repeated. Yep, another question.
I have a question about this. I didn't really understand why the
Yeah, that's a really good question. So in general, you can think about the more you sample a period, like the narrower these peaks are going to be. So what I'm interpreting from this is that they have a lot of samples on things like a day time scale, but they don't have as many samples on like these longer period time scales. So it's almost like an uncertainty in how well the window function like understands each of these peaks. So this particular data set might be only like 5 or 10 years or something. So it doesn't have as much of a good sampling of this longer period thing. And this is a general pattern that you'll see in these window functions is that when you get to like smaller periods, shorter periods, usually we have those periodicities sampled a lot better. Yeah. The reason mathematically why you see this is that usually we plot these in frequency space, and they're going to be uniform in frequency space. And then when you translate it to period space, you have a 1 over frequency, and that sort of stretches out the longer periods. Good question. Yeah, so we've talked about the 1-day period, its aliases at 1 over n, and then the 365-day peak. What else do you see?
Something like 15, 14.
Yeah, exactly. This guy here. So I'm gonna ask you to explain that one because I didn't know how to explain it when I first saw this. But yeah, some thoughts so Jake in his paper says that this is probably related to patterns of scheduling. So maybe the telescope's only on the instrument's only on the telescope every 2 weeks or something like that. The other thing that struck me is that it could be related to the phases of the moon. If the moon's period is 28 days, so for whatever reason, if you observe during 2 particular phases of the moon, where you couldn't observe during 2 phases of the moon for whatever reason, that might imprint this the same peak, but I don't know exactly what it is. But yeah, exactly.
I also just don't think I understand why the peaks prior to 1 day or like that are faster than 1 day, why they have that shape.
Yeah, that's a really good question. So I'm gonna have you explore this in one of the problems a little bit too. But the sort of conceptual answer that I can try to give you is that so when I was answering Tony's question, I was thinking about sort of the separations that occur frequently between successive data points. So you could think about like a classic separation between data points is like half the day or half the night, because you might observe one at the beginning and one at the end of the night. And then again, you might observe something at, a third of the way through the night. But the reason that they sort of go down is because it's going to be sort of less and less common to get these like these smaller. Yeah. So yeah, good question. Okay. So now that we've looked at this window function to death, I want to show you how it actually imprints on a real data set. So this is the same window this is the same window function, but it's now in frequency space. And here's the light curve that it's been imprinted on. So this light curve, just to sort of give you the answer, just has a single peak. So it's only one sinusoid, and the true frequency of the sinusoid is here. So this is like the real underlying signal, and all of these are aliases. And then this little inset zooms in on this part here, and you can see that there's also these additional aliases. So these are due to the window function peak at 1 year, and these are due to the window function peak at 1 day. So the last thing I want to do before I let you loose for the problem session is I want to do a think, pair, share about why these peaks are symmetric on either side of the same frequency. So I'll give you 2 minutes to think about it by yourselves, and then share with a neighbor. And then if you want to, I'll ask a group or two to share what they're thinking. Okay, so take 2 minutes and just think about it by yourself, and I'll let you know when it's time to talk to your partner. Okay, at this point, I'm gonna have you talk to your partner. And I said this yesterday, I'll remind you, I'm not necessarily expecting you to like get the answer to this or like you know, have a brain blast moment and be like, oh my God, I'm a genius, I figured it out. I just want you to think about it before I sort of give you the answer. So don't worry if it's not obvious. Okay, so take 2 minutes to talk to a partner.
Yeah, that would be to the left. Yeah. Well, yeah. This makes sense.
All right.
Yes, I've done.
Okay. So before I ask everybody to share, so thumbs up if you think you got it, thumbs to the side if you're unsure, thumbs down if you have no idea. All right. We have a lot of thumbs to the side. Cool. Anybody feeling brave and wanna show their thumb?
I was saying that it looks like something happened at Fmax and then you get like a ring down effect.
Yeah. Yeah, that's definitely true. Are you a gravitational wave person?
No.
Okay. Cool. Anybody else want to share what they're talking about?
We just kind of Waverly said that it's something about sliding like convolution function or intrinsic data set be symmetric. It's that when you hit one side of it, it's alias, and you hit the other side of it, it's alias. So you got like this peak and then you get either sides of the symmetric function.
Yeah. So you've got some good elements in the answer. I think what you were saying about what both of you were saying about the sort of like the main peak being the like intersection of the window function, like sliding past this sort of main thing, and then you've got these like bring down type things on either side. It's definitely true. So there's one sort of piece that I think will make it come all together for you. Anybody else have a thought? Yep.
We thought that it might have to do something with the observing cadence, like this thing is being observed multiple times over a night, over multiple nights. Then maybe there's something in there with the sampling cadence over both like one night, not observing it every 10 minutes, but plus or minus something, and then difference with other nights observing it.
Yeah, that's interesting. So you're thinking that maybe there's some other feature in the window function that's like not necessarily showing up here. That's a really good thought. So I think, again, I didn't expect anybody to sort of like figure out what was going on. But so what's actually sort of causing this is that sneakily I showed you the power spectra and not the Fourier transform of the window function. So the window function in Fourier transform actually has symmetric peaks on this side in this negative area. So when you slide that past the true, like, even if you think of the signal as like a delta function at some, positive value, you're going to be sliding that whole cone past this particular peak. And then when you take the power spectrum of that, those peaks will all show up. Cool. So thank you so much for all of your efforts on that. I really appreciate it. Yep.
I'm honestly having difficulty, so I get mathematically if it's involved, you get that. But if the signal, you have a signal that's like repeating every 2.58 hours, how can you see frequencies other than that? Like based on how you're observing, I just can't like understand, especially like symmetric at, I guess, twice two, like every 5 hours and every 1.25 hours.
Yeah. So it's basically, you can think of it like you are introducing periodicity in your data by the way that you're observing. So if you were to just only observe every hour, you have periodicity in your data. Even if you were to observe a straight line, every hour, you're introducing periodicity. And the way that the Fourier transform mathematically works, and the Lomb Scargle periodigram by extension, it's going to pick up all of that stuff. So you're going to see not only the true underlying frequencies that you have, but also these sort of products of your window function.
If you're observing every hour and the signal only pops up every 2.5 hours, say you start observing at hour 0, but the signal is at hour half, and if your cadence is 1 hour, then you never see a signal.
So
am I just like being too naive?
No, I think you're talking about a different. So you're talking about Nyquist sampling, I think, which is a sort of different thing. So if you observe at like a product of the frequency, so if your signal is 2 hours and you only observe it every 2 hours, you're never going to see a signal, right? You're always going to see it when it's at this sort of minimum. So that's a fundamentally different issue to do with like Fourier analysis that you have to sort of keep in mind. So that's separate from this issue of like aliasing when your window function frequencies aren't a function of the underlying frequency. Yeah, but yeah, that's a good point. I didn't talk about Nyquist sampling at all in this question.
It's about how the window function affects the peaks that we see on the slide. Is that representative of the actual intensity that we're seeing being changed? Or so, like for example, if I'm thinking of like a separate variable or something like that, somebody who we know, got a pretty good standard of the intensity of spectrum. So is changing the window function for that change the way we see the intensity?
Yeah, good question. So this, there's also, I probably should have included a plot from Jake's paper that actually shows you what the signal looks like in time space. So that's, I think, figure 1 or 2 in the paper, so you can go check that out if you want. But basically, it's not going to affect what you're seeing in time space. It's only going to affect the Fourier transform that you observe. So if you take the Lomb Scargle periodogram, you're going to see this pattern of peaks. But hopefully this is convincing you that it's important to understand how the Lomb Scargle periodogram works under the hood. Because if you saw this and you sort of had no background in like window functions and reasoning about the convolution and all this type of stuff, you would say, oh my God, there's like 17 different frequencies in this thing. What an interesting signal. And you'll see all the time, this is still really hard, and people like, I don't want to say mess it up, but sort of interpret it in a way that ends up being proven incorrect later. in exoplanets all the time. Like people will be like, oh, we found a planet with a period of 180 days. And then the whole community is like, but sometimes it is. But yeah, so these types of things are really important to think about. And they mess up experts all the time. Okay, so yeah, so let me give you, I think like 45 minutes. Is that how much time we have to work on the problem set? So I've got 4 problems. I actually removed the 5th problem. So if you finished the 5th problem yesterday, I'm sorry. But yeah, so the first problem is a derivation problem to prove that I'm a real mathematician. The second one is about sort of getting intuition with convolution, like thinking about doing it by eye and then checking it by plotting it. The third one I think is my favorite, where you're going to make your own realistic observing conditions. So you're going to actually observe a signal and see how the Lomb Scargle periodogram changes depending on the window function that you use. And then the fourth one again is sort of trying to visualize convolution and all this type of stuff. So I think if I were you, I would prioritize, I would probably do question 3 first, then prioritize 1 and 2, and then if you have extra time, go on to 4. And I said, if you get all of that done, then you can work on a cool visualization of the convolution theorem that I can use in my lesson next time. Okay, be free.